The JHS AT Plus is a great distortion pedal. But have you ever wondered what exactly the toggle switch does? It's up here, right? The manual says switching between 25, 50, and 100 watt modes. But what's exactly going on? Well, hi, I'm JHS of Phase 2 Music, and today we will investigate what these three modes really do. We will start by listening to some clips with the pedal using these modes, and I will set the drive knob at 12 o'clock and the volume to match my clean sound in the 100 watt mode. First, here's my clean reference sound. So let's listen to what that toggle switch does. Okay, so we hear volume differences, but what's really happening, and can we see what we heard? This is a typical overdrive distortion pedal block diagram. It has an input filter, a saturation stage, and an output filter. Today we will focus on the saturation stage. In a previous video we discussed how distortion pedals often used hard clipping devices on the output of the op amp. If this is true, then is this what the power modes are doing? Well, these plots show the pedal's outputs with the sine wave input. The x-axis is time and the y-axis is the pedal's output voltage. Note we can see three different levels: 25 watt, the 50 watt, and the 100 watt setting. These plots show different output levels which we heard, but they don't reveal the clipping thresholds because the volume knob is turned down and the EQ and air controls are still shaping the signal. With the volume, air, and EQ controls at maximum, we can see what the wattage modes really do. The 25 watt mode clips at about plus or minus 0.7 volts, similar to a silicon diode. The 50 watt mode is clipping at about plus or minus 1.9 volts, about something like that, like an LED. And finally, the 100 watt mode is at plus or minus 4 volts, a little over that, where the op amp output is probably becoming the clipping device. Well, based on the measurements, this is my interpretation of the three clipping modes. I'm only showing the clipping stage, and I'm also not showing the exact switching network itself. The 25 watt mode are silicon diodes, 50 watt seems to be LEDs, and the 100 watt is op amp limiting. Okay, so the pedal uses three different hard clipping devices which change the perceived volume. But is that all they do? I will replay the riff but match the volumes. Do the clipping modes still sound the same? Although there may be slight differences, maybe we're just driving the pedal too hard. We could drive the pedals with a smaller input like finger picking. Okay, we'll give that a go. The differences are noticeable but subtle. Now, many guitars reduce the signal going into the distortion pedal with the guitar's volume knob or volume pedal. Let's see if that makes the clipping modes easier to distinguish. I'll repeat strumming and finger picking examples, again matching the output volumes. Well, that worked. With this input signal reduced, the op-amp clipping mode stays cleaner whether I finger pick or strum. In LED mode, finger picking remains clean while strumming pushes the circuit into breakup. Finally, in silicon diode mode, the signal still clipped regardless of how I play. Now, in my setup, achieving this required about 35 dB of attenuation. The exact amount isn't universal. It depends on your guitar, pickups, playing style, string setup. You get the idea. Your mileage may vary. So why does changing your playing style or input level change the sound? To answer that, I captured 6 representative playing examples and plotted their waveforms on a common scale. Okay, looking at the graph, it seems like several waveforms are like missing. Well, they're actually there, but their amplitudes are so small, they look like they're at 0. To reveal these smaller signals, first we extract the waveform envelope, leaving only the signal's changing amplitude. That's done on the lower trace. It's still hard to see the small signals, so on a linear scale, the larger signals still dominate the display, making the smaller ones difficult to see. But a logarithmic scale compresses the larger signals while expanding the smaller ones, making all 6 playing examples easier to compare. So now we can see all the waveform examples. The first 3 examples use 35 dB of attenuation I talked about, similar to what using my volume pedal. Finger picking, strumming, hard strumming, and then the next 3 use full guitar output without the volume pedal reduction. More finger picking, more strumming, and finally some hard aggressive strumming. Although I rarely play this hard, it's used for showing the full operational range. We've seen the signals entering the pedal. Now let's see how those same signals change the amount of distortion the pedal produces. Let us start with just LED mode. These 2 plots show how the pedal behaves as the input level increases. The x-axis is the signal going into the pedal, measured in dB volts, the same units we used for the guitar envelope diagrams. Coincidence? I think not. The top plot shows the pedal's output level, while the bottom plot shows the total harmonic distortion, or THD, which is a measure of the distortion. At first, increasing the input produces a linear increase in output, but as the pedal begins to saturate, the output stops rising while the THD increases rapidly. This is the transition from a mostly clean signal into distortion. One way to identify where this transition begins is by looking at the point where the THD reaches minus 30 dB. I'm going to refer to this as the edge of breakup. A few decibels below it, the sound is generally clean, while a few decibels above it, the distortion becomes much more noticeable. This is not an industry standard definition. It's simply a measurement I have found useful for comparing pedals in a consistent way. Now let's show all 3 clipping modes, and we can see what we heard. Each mode begins clipping at a different level and reaches a different maximum output. The silicon diode begins clipping first and produces the lowest output voltage. The LEDs allow for a larger input signal before clipping and produce a higher maximum output. Finally, the op-amp allows the largest input signal before clipping and therefore produces the highest maximum output. Before we listen to audio examples, there's one final graph set I'd like to explain. The upper plot shows the input envelopes for the different playing styles, while the lower plot shows how the pedals respond to every possible input. It may not be obvious, but these 2 plots are directly connected. The vertical axis of the envelope plot is the pedal's input level in dB volts, and the horizontal axis of the THD plot is that same input level. In other words, the y-axis of the upper plot becomes the x-axis of the lower plot. This lets us map any playing style directly onto the pedal's distortion response. This strumming example occupies approximately this range of levels. We can locate that same range along the input axis of the THD plot and see how much distortion the pedal produces at that level. For op-amp clipping, since the signal is below the edge of breakup, it will not be distorted. But when the clipping mode is switched to silicon diode clipping, now the playing range is above the edge of breakup and the sound will be more distorted. Now let's listen to some musical examples. These recordings represent the same playing styles used for the measurements. As each example plays, the corresponding envelope and operating range will be highlighted. As you listen, notice how the amount of distortion changes as the signal moves through the different clipping regions. To make those changes easier to hear, the volumes of the examples have been matched yet again. In summary, with the guitar's current setup, by changing how I play, moves the operating point from here with finger picking, to here with typical strumming, and to here with hard strumming. In actual playing, your guitar's range can move anywhere within this range, as guitarists rarely play using only one playing technique. In practice, the signal into a distortion pedal can vary wildly depending not only on your playing technique, but the guitar, its pickups, its volume, tone knobs, and any pedals before the distortion pedal. So the key takeaways from this video are: the clipping voltage in devices sets where the clipping begins. The guitar playing style and upstream pedals determine the pedal's operating point. That operating point determines the amount of distortion, and that clipping voltage limits the maximum output level available. This video focused on 3 clipping methods: op-amp clipping, silicon diodes, and LED diodes. But they represent only a small sample of the clipping circuits used in guitar pedals. Future videos will continue to investigate how different guitar pedal designs influence the sound and feel guitarists experience. If you found this interesting, please click like, subscribe, share. It really helps the channel. You can also visit phase2music.com to learn more about my pedals. Until next time, hey, just keep on jamming.